The hero of today's story is Isaac Newton, one of the greatest minds in the history of humanity, a scholar whose discoveries laid the foundations of modern physics and mathematics. England in the mid-17th century was a country gripped by turmoil and uncertainty. The civil war between the supporters of King Charles I and Parliament was tearing society into two warring factions. Battles swept through the counties, villages burned, and people lived in constant fear of what tomorrow would bring. At the same time, while the king's cavalrymen clashed with Oliver Cromwell's forces, ordinary life continued in the small village of Woolsthorpe in Lincolnshire, simple people trying to survive turbulent times far from the great events of history. On Christmas night in 1642, according to the Julian calendar then in use in England, a child was born in a modest stone manor house, a child who would forever alter the course of the history of science. Hannah Eiskopf, a young widow whose husband had died just 3 months earlier, gave birth to a son. The boy was born prematurely, extraordinarily small and weak. Local midwives gave him no chance of survival, and the servants sent to fetch linen for the newborn reportedly did not hurry at all, convinced the infant would die before they returned. Yet the fragile child proved surprisingly tenacious in the fight for life, and a week later was christened with his father's name, a father he would never know. Isaac Newton, son of an illiterate but prosperous farmer, began his long and remarkable journey through life. The name Isaac derives from Hebrew and means, "he who laughs," which in the context of the boy's later fate sounds almost like bitter irony. His earliest years passed in the shadow of loneliness and rejection. His mother, the only person close to him, remarried just 3 years after his birth. Her chosen partner was Barnabas Smith, a wealthy pastor from a nearby village, more than 30 years her senior. The clergyman set a ruthless condition, the cruelty of which is hard to comprehend today. In the prenuptial agreement, he demanded that Hannah leave her 3-year-old son and move in with him, without the child from her first marriage. Little Isaac was placed in the care of his maternal grandmother, Marjorie Eiskopf. For the next 8 years he grew up in the family manor at Woolsthorpe, deprived of his mother's presence, whom he could only sometimes glimpse from a distance. His grandmother, though she provided him with a roof over his head and food, could not replace parental love and warmth. She raised her grandson with strictness, attending to discipline, but not to his emotional needs. She also forbade him from playing with children from nearby farming families, considering them too lowly for the offspring of landowners. As a result, the boy grew up in almost complete isolation, thrown entirely upon his own company. These early experiences left deep marks on young Isaac's psyche. The sense of abandonment and rejection by his mother, whose presence he so desperately needed, shaped his character in a way that would weigh upon his entire later life. The boy learned not to trust people, and not to rely on anyone but himself. He developed a deep distrust of others, and a tendency toward emotional distance. His temperament grew increasingly volatile and unpredictable. The outbursts of anger that visited him in childhood would accompany him throughout his life, making him a difficult man to live with. He harbored particularly intense hatred toward his stepfather, whom he blamed for the separation from his mother. Surviving notes show the adult Newton confessing his childhood sins, among them a threat to burn down Barnabas Smith's house with him inside it. The force of that hatred speaks to the depth of the wounds his motherless childhood had inflicted. Yet fate spared him the necessity of enduring the hated stepfather for long. After 8 years of marriage, Barnabas Smith died, and Hannah returned to the family home at Woolsthorpe. One might suppose that his mother's return brought the 10-year-old Isaac a well-deserved comfort, but the reality proved more complicated. Hannah did not return alone. She brought with her 3 children from her marriage with the pastor, a son and 2 daughters. For Isaac, this meant yet another disappointment and a deepening sense of rejection. Instead of regaining his mother's undivided love, he was forced to share it with half-siblings whom he regarded with mutual dislike. In his later notes, one can find traces of the deep resentment he harbored toward his half-brother and sisters. The only positive aspect of this difficult period turned out to be the library left behind by the deceased stepfather. Barnabas Smith, as a clergyman, had amassed a considerable collection of books, chiefly theological in content. Young Isaac, lacking the company of peers and shut within his own world, turned to those volumes. He devoured the religious works with extraordinary attention, which planted in him the seeds of deep piety that would accompany him throughout his life. Faith in God and an interest in theology became an inseparable part of his identity, and in later years he devoted as much time and energy to biblical studies as to scientific research. The period of relative stability following his mother's return did not last long, however. When Isaac turned 12, Hannah decided to send him to school. The boy left Woolsthorpe and went to the nearby town of Grantham, where a new phase of his life was to begin. It was a turning point that would open before him the road to greatness. Although its beginnings in the new place proved anything but promising, young Newton, shaped by years of loneliness and emotional difficulties, faced the challenge of finding his place among strangers in an environment that required skills he had never had the opportunity to develop. The school in Grantham was to become the site of his first intellectual triumphs, but before that came many difficulties and disappointments. The grammar school in Grantham, to which 12-year-old Isaac went, was a typical English educational establishment of the time. It taught chiefly Latin, which remained the language of scholarship and diplomacy, as well as basic Greek, rhetoric, and arithmetic. The curriculum rested on the classical texts of ancient authors, and the teaching methods did not differ from medieval patterns. For a boy raised in the isolation of a country manor, encountering a group of peers came as a shock for which he was unprepared. His first months at school proved a genuine catastrophe for Isaac. The boy, who had never learned to function among people, could not find his footing in the new environment. His academic results were dismal, and by the end of his first year, he ranked second to last in the class. Teachers saw no particular talent in him, and his peers treated him as an oddity and an outsider. Isaac responded to rejection in the only way he knew. He started fights, provoked conflicts, and regularly quarreled with classmates and teachers alike. His temperament, formed by a painful childhood, asserted itself with full force. Relations with the opposite sex were equally difficult, though for entirely different reasons. Isaac showed no interest in girls, who repaid him with the same indifference. A memory survives from a woman who, in old age, claimed that as a young girl living nearby, she had been the object of young Newton's affections. But it is hard to verify the reliability of these recollections, set down many decades after the events, when Newton was already a famous scholar. What can be stated with certainty is that Isaac, throughout his long life, remained alone and never married. His interest in women, if it ever existed at all, faded entirely as the years passed. Isaac's living situation in Grantham proved, however, surprisingly beneficial for the development of his true talents. The boy was lodged at the home of a local apothecary named William Clark. An apothecary's shop in 17th-century England was a special place, combining the functions of a chemist's, a laboratory, and a physician's consulting room. Mr. Clark ran his own workshop, where he prepared mixtures and medicines according to the recipes of the day. For young Isaac, who until then had been able only to observe nature and reflect in solitude, access to a real laboratory opened a completely new world. The boy eagerly helped the apothecary prepare medicines, learning the basics of chemistry and the craft of experimentation. He observed how different substances reacted with one another, how they changed in color, consistency, and properties. These practical experiences kindled in him a passion for experiment that was to become the foundation of his future scientific method. Unlike many later theorists, Newton always remained an empiricist, for whom experience and observation were the highest authorities in understanding the world. The stay at the apothecary's house also revealed the extraordinary constructive abilities of young Isaac. The boy began to build various mechanical devices, displaying ingenuity and precision far beyond his years. He constructed, among other things, a water clock driven by a steady flow of water, which worked with surprising accuracy. This device was so reliable that visitors to the apothecary would set their watches by it. He also built kites, to which he attached lanterns, flying them over the town at night and causing residents to speculate about supernatural phenomena. He also constructed miniature mills and mechanical vehicles, each demonstrating his exceptional ability to understand how machines work. These pursuits in the apothecary's workshop meant far more to Isaac than his school education. It was here, and not in the classroom, that he developed his intellectual potential. Working with concrete objects and mechanisms taught him cause and effect thinking, perseverance in solving problems, and precision in completing tasks. Each toy or device he built required analysis, planning, and the patient refinement of details. Those skills, acquired in building clocks and mills, were to prove invaluable in his future scientific investigations. Gradually, Isaac's school situation began to improve. It is hard to say today exactly what caused this transformation. Perhaps the boy simply adapted to his new environment, or perhaps he discovered that success in learning could be a form of revenge on the peers who had rejected him. Whatever the cause, from his second year Newton began climbing the school hierarchy. His results improved steadily, and teachers began to see in him a potential they had not previously noticed. The headmaster, Henry Stokes, became a particularly strong advocate of young Newton, seeing in him a pupil of exceptional promise. The period of quiet study and development was, however, abruptly interrupted by a decision of his mother. Hannah Newton decided that her son had spent quite long enough over books, and that the time had come for him to take responsibility for the family farm. Isaac was now 16, and in his mother's eyes old enough to manage the estate at Woolsthorpe. He was therefore recalled from school and returned to the family home, where duties entirely unsuited to his temperament and interests awaited him. Young Newton found himself facing the prospect of a life as a country squire. He was to herd sheep, oversee farm work, sell grain at markets, and attend to 1,000 minor affairs connected with running an estate. For a boy whose mind was perpetually occupied with the puzzles of mechanics, chemistry, and mathematics, it was a depressing prospect. Isaac made no secret of his disgust at the duties imposed on him, and performed them with such demonstrative reluctance that it drove the household to despair. Anecdotes survive that illustrate his complete unsuitability for the role of farmer. Sent to market to sell farm produce, he forgot all about business, and sat under a tree for hours, absorbed in reading or reflection. Instead of watching over the sheep, he would construct miniature devices or solve mathematical problems in his head, while the animals wandered across the fields, causing damage to neighbors. This was not conscious and deliberate rebellion, but rather the manifestation of a deep inability to occupy himself with things that did not interest him. Isaac's mind simply refused to engage with activities he considered a waste of time. The situation was becoming increasingly unbearable, both for Isaac himself and for his family. His mother and grandmother saw that the boy was utterly unfit for running a farm, and that his presence at home caused more problems than benefits. At the same time, Headmaster Stokes persisted in his efforts to persuade Hannah to allow her son to continue his education. He saw in Isaac a pupil of extraordinary ability, whose squandering on agricultural tasks would be a genuine crime against his talent. To the voice of the headmaster was soon added a voice from within the family. William Ayscough, Isaac's maternal uncle, who had himself graduated from Cambridge, supported the idea of further education for his nephew. What is more, he offered financial support that would allay Hannah's concerns about the cost of schooling. These arguments, combined with the daily observation of her son's complete uselessness at farm work, eventually convinced the mother. After several months of the failed experiment of turning Isaac into a farmer, she agreed to his return to the school in Grantham. For young Newton, it was a pivotal moment. He returned to school with a completely new attitude. He now knew that the alternative to learning was a life he could not endure. The fear of returning to herding sheep and managing the estate became a powerful motivation to achieve academic success. From that point on, he applied himself to study with a zeal he had never shown before. His results quickly shot upward, and Headmaster Stokes proudly held him up as a model for other pupils. In his final years at Grantham, Isaac prepared intensively for the entrance examinations to university. His goal became Cambridge, the oldest and most prestigious institution in England. For a boy from a provincial village, who had recently ranked second to last in his class, it was an ambitious dream, but, as would prove to be the case, a wholly realistic one. The school in Grantham had given him not only knowledge, but also the certainty that his place was among scholars, not among the sheep in the meadows of Woolsthorpe. In June 1661, 18-year-old Isaac Newton crossed the gateway of Trinity College, Cambridge. This university, founded as early as the 13th century, was one of the two most important institutions in England and a forge of the kingdom's intellectual elite. For a young man from provincial Lincolnshire who had recently been herding sheep in the fields of Woolsthorpe, it was entry into a completely different world. A world of ancient ivy-clad walls, scholars in flowing gowns, and libraries harboring knowledge accumulated over centuries. Isaac's social status at university was, however, far from privileged. He was admitted as a so-called subsizar, that is, a student of the lowest category, who paid for his upkeep by performing services for wealthier fellow students and lecturers. This meant cleaning rooms, serving meals, polishing boots, and carrying out other menial tasks. For a young man of proud and prickly character, it must have been a humiliating experience, though doubtless no worse than the prospect of a farmer's life. Curiously, Isaac's mother had sufficient means to pay for her son's status as an ordinary student, but for reasons unknown, refused to provide this support. Perhaps she still harbored resentment at his refusal to take over the family estate. Trinity College, in which Isaac was to spend the next 35 years of his life, was the largest and wealthiest of the Cambridge colleges. Its name, signifying the Holy Trinity, pointed to the religious roots of the institution. Cambridge, like Oxford, had grown from the tradition of medieval cathedral schools, and had remained closely tied to the Church over the centuries. Even after the Reformation, which broke the bonds with Rome, the university retained the character of a deeply religious institution. Students were required to attend services, and an academic career was practically closed to those outside the Anglican Church. The curriculum with which young Newton came into contact was deeply rooted in the medieval scholastic tradition. Its basis was the works of Aristotle, the Greek philosopher who had lived almost 2,000 years earlier. Students delved into Aristotelian logic, ethics, rhetoric, and natural philosophy, treating the writings of the ancient thinker almost as revelation. In 17th-century Cambridge, Aristotle remained an unquestioned authority, and questioning his views was seen as a sign of intellectual arrogance or even heresy. One of the fundamental elements of the Aristotelian worldview was geocentrism, the conviction that the Earth stands motionless at the center of the universe, and that the sun, moon, planets, and stars revolve around it in perfect circles. This cosmological model, elaborated in antiquity by Ptolemy, had provided the basis for European understanding of the cosmos for over 1,000 years. The Church had adopted it as consistent with biblical teaching, and anyone who dared to challenge it risked serious consequences. Still vivid was the memory of Galileo, who barely 2 decades earlier had been compelled by the Inquisition to publicly recant his views on the motion of the Earth. Young Newton quickly discovered that the official curriculum did not satisfy him. The lectures on Aristotelian philosophy seemed to him antiquated and divorced from reality. Instead of uncritically accepting the doctrines imposed on him, he began independently seeking other sources of knowledge. In his notebook from those years, he wrote down a famous sentence in Latin which became the motto of his intellectual independence. "Plato is my friend, Aristotle is my friend, but my greatest friend is truth." These words, echoing an ancient maxim attributed to Aristotle, expressed the young student's determination not to submit to any authority in his search for truth about the world. In the seclusion of his room and in the dim passageways of the university library, Isaac immersed himself in reading works that did not appear on the official curriculum. He reached for the writings of René Descartes, the French philosopher and mathematician, whose mechanistic vision of nature offered a radical alternative to Aristotelianism. Descartes perceived the world as a great machine operating according to strict mathematical laws that the human mind is capable of discovering and describing. This perspective fascinated Newton deeply and exerted a lasting influence on his own approach to science. He also studied the works of Johannes Kepler, the German astronomer who, on the basis of observations by the Danish scholar Tycho Brahe, had formulated revolutionary laws of planetary motion. Kepler had shown that planets do not move in perfect circles, as Aristotle and Ptolemy had taught, but in ellipses with the sun at one focus. This was another blow to the edifice of traditional cosmology, and another step toward a new picture of the universe. Newton also absorbed the works of Galileo, the Italian scholar whose telescopic observations had finally undermined the Aristotelian division between the perfect heavens and the imperfect earth. Galileo had discovered mountains on the moon, spots on the sun, the phases of Venus, and moons orbiting Jupiter. Each of these discoveries struck a blow at the ancient system of the world and prepared the ground for a new science of nature. These solitary studies, conducted in parallel with the official curriculum, shaped Newton as a scientist. He learned to accept nothing on faith, to test propositions through observation and experiment, to pose his own questions and to seek answers to them. He also developed his mathematical skills, advancing far beyond what was taught at university. Mathematics was to become his principal tool in discovering the laws governing nature. In 1665, as Newton was completing his bachelor's degree, the shadow of death hung over England. The plague, which had visited Europe in waves of epidemics for centuries, returned with unprecedented force. The pestilence that passed into history as the Great Plague of London killed almost 100,000 inhabitants of the capital within a few months, roughly a quarter of its population. From London, the epidemic spread to the provinces, reaching Cambridge as well. The university decided to close and sent students home. For most, this was an educational catastrophe, interrupting their studies and severing their contact with teachers and libraries. For Newton, it proved to be something else entirely. The 22-year-old graduate returned to his native Woolsthorpe and spent the next 18 months in isolation, far from the university duties and lectures that bored him. Rather than hindering his work, the enforced quarantine gave him something priceless: time and quiet for thought. In the seclusion of the country manor where he had spent his unhappy childhood, Newton made the greatest discoveries in the history of science. This period, which he himself later called his most fruitful years, passed into history as the Annus Mirabilis, or Year of Wonders. The term, though it speaks of a single year, in reality covers the entire period from the summer of 1665 to the spring of 1667. During this time, working in complete solitude, without access to libraries or laboratories, the young scholar laid the foundations of modern physics, mathematics, and optics. His mind worked with extraordinary intensity, leaping from one problem to another, perceiving connections where no one else had seen them. He conducted experiments with prisms, investigating the nature of light. He developed new mathematical methods that made it possible to describe change and motion. He reflected on the forces governing the motion of bodies on earth and in the heavens. It was at Woolsthorpe, according to tradition under an apple tree in the orchard, that he began to formulate the questions that would lead him to the discovery of the law of universal gravitation. The young man who had returned home before the epidemic was not yet the Newton the world knows, but when the plague abated and the university reopened its doors, it was a genius who returned to Cambridge, a genius whose discoveries were to transform the face of science. Among the many questions that occupied young Newton's mind during his stay at Woolsthorpe, the nature of motion held a special place. Since the time of Aristotle, philosophers had wondered why bodies move as they do and not otherwise. The Greek thinker had taught that motion requires continuous action of a force, and that a body left to itself naturally tends toward rest. For almost 2 millennia, this intuitive though erroneous concept had dominated European thought. Only Galileo had begun to challenge it, conducting experiments with balls rolling down inclined planes, and concluding that a body in motion will continue to move if no force opposes it. Newton went far beyond Galileo. In the seclusion of his room at Woolsthorpe, he formulated 3 fundamental principles describing the motion of bodies, principles that to this day form the basis of classical mechanics. The first of them, later known as the principle of inertia, stated that a body remains at rest or moves in a uniform straight line unless acted upon by an external force. This was a radical break with the Aristotelian view that motion requires continuous maintenance. Newton showed that it is not motion, but change of motion that requires explanation. The second law of dynamics expressed the relationship between force and motion in a precise, mathematical way. Newton stated that the change in motion of a body is proportional to the applied force and occurs in the direction of that force. The greater the force, the greater the acceleration, and the greater the mass of the body, the harder it is to set in motion or to stop. This seemingly simple relationship proved to be the key to understanding innumerable natural phenomena, from the falling of stones to the motion of planets in their orbits. The third law, called the law of action and reaction, stated that every force is accompanied by a force equal in magnitude but opposite in direction. When a horse pulls a cart, the cart pulls the horse with equal force. When the earth attracts an apple, the apple attracts the earth with identical force. This fundamental symmetry of interactions pervaded all of nature and made it possible to explain phenomena that had previously seemed entirely unconnected. These 3 laws, though they may sound familiar and almost obvious today, represented in the 17th century a genuine intellectual revolution. Newton achieved something philosophers had dreamed of for millennia. He created universal laws that held always and everywhere, regardless of whether they described falling stones, flowing rivers, or flying cannonballs. Nature ceased to be a chaotic collection of unrelated phenomena and became an ordered cosmos governed by unchanging mathematical laws. Newton's most revolutionary achievement, however, was applying these same principles to the heavenly world. Since ancient times, people had believed that the heavens were governed by entirely different laws than the earth. Stars and planets were thought to be perfect bodies, moving in perfect circles, composed of unearthly matter. Newton dared to ask a question that had not previously occurred to anyone. What if the same force that causes an apple to fall from a tree was also responsible for keeping the moon in its orbit? The story of the falling apple that inspired Newton to discover the law of gravitation is one of the most famous anecdotes in the history of science. Newton himself told it toward the end of his life to guests and biographers, though the details varied from one account to another. Some claimed the apple fell on his head, others that he simply observed fruit dropping in the orchard. Whatever exactly happened, it is certain that Newton was indeed reflecting on the connection between the force pulling apples toward the earth and the force keeping the moon in its orbit. Newton's reasoning was at once simple and brilliant. An apple falls to the earth because the earth attracts it. The moon is also subject to the earth's attraction, but does not fall, because at the same time it moves sideways. If the moon were stopped in its place, it would plunge toward the earth like a gigantic apple. Yet its sideways motion causes it continually to miss the earth, falling around it as it were. The moon's orbit is thus the result of combining 2 tendencies, gravity toward the earth and the tendency to continue moving in a straight line. Newton asked himself how the force of attraction varies with distance. Intuition told him that the farther from the earth, the weaker the attraction, but according to what rule? Using available data on the distance of the moon from the earth and the period of its revolution, the young scholar performed calculations that led him to a fundamental conclusion. The force of gravity decreases in proportion to the square of the distance. When the distance doubles, the force is reduced 4-fold. When it trebles, the force weakens 9-fold. This simple mathematical relationship proved to be the key to understanding not only the motion of the moon, but the entire planetary system. Newton realized that the same force that attracts apples and stones keeps the planets in their orbits around the Sun. The Sun attracts the Earth just as the Earth attracts an apple, only on an incomparably larger scale. Kepler's laws, which described the motion of the planets in an empirical manner, finally found their theoretical explanation. Elliptical orbits, the varying speeds of planets, the precise relations between distances and orbital periods, all of it followed from one simple law. Newton formulated this law in universal terms. Every body in the universe attracts every other body with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. This law of universal gravitation held everywhere, from grains of sand to the most distant stars. The universe proved to be unified by one force, operating unchangingly at every point in space and time. The consequences of this discovery were immense. The division between the imperfect Earth and the perfect heavens, which had shaped human thinking about the cosmos for millennia, proved to be an illusion. The moon and an apple were subject to the same laws. Planets and cannonballs moved according to the same principles. Newton demolished the wall separating the earthly world from the heavenly and showed that the entire universe is one great machine operating according to strict mathematical rules. To describe these discoveries precisely, Newton needed a new mathematical language. Traditional geometry and algebra were insufficient for describing phenomena in which quantities changed continuously. How does one describe the velocity of a body, which is different at every instant? How does one calculate the area of a figure with curved boundaries? Newton created an entirely new branch of mathematics, which he called the method of fluxions. This same calculus, developed independently by the German scholar Gottfried Wilhelm Leibniz and named by him the differential and integral calculus, became the foundation of modern mathematics and the natural sciences. All these revolutionary ideas were born in the mind of a 22 or 23-year-old, working in the isolation of a country manor. Newton accomplished more in the space of a few months than most scholars do in a lifetime. Yet for many years he told no one about it. The notes from Woolsthorpe went into a drawer, and the young genius returned to university to continue his official academic career. The world would not learn of his discoveries until many years later, when circumstances forced him to reveal what he had so carefully concealed. Besides the questions of mechanics and gravitation, the mind of young Newton during his stay at Woolsthorpe was also absorbed by the nature of light. The question of what light is and where colors come from had fascinated philosophers since antiquity. Aristotle had taught that colors arise from mixtures of light and darkness in varying proportions, with white being the pure form of light, while other colors were its contaminations. This view, though entirely wrong, had survived for nearly 2 millennia and still dominated in the 17th century. Newton resolved to investigate the nature of light by experimental rather than speculative means. In 1666, he purchased at a Woolsthorpe fair a glass prism, a 3-sided piece of transparent glass that served at the time chiefly as a curiosity and toy. Scholars knew that a prism refracted sunlight and produced a colored streak resembling a rainbow, but the phenomenon was regarded as a curiosity rather than a key to understanding the nature of light. Newton conducted a series of carefully planned experiments in his darkened room. He covered the window, leaving only a narrow slit through which a thin beam of sunlight entered. He then placed the prism so that the beam passed through the glass and fell on the opposite wall. On the white surface appeared an elongated band of colors, from red through orange, yellow, green, and blue, to violet. This phenomenon, known as the spectrum of light, was not in itself new. What was new, however, was what Newton deduced from it. The traditional explanation held that the prism somehow modified white light, adding colors to it or tinting it. Newton suspected something entirely different. He hypothesized that white light is not a pure, simple substance, but a mixture of all colors, which the prism merely separates. To test this, he designed an experiment that has passed into the history of science as a decisive proof. He placed a second prism in such a way that a single band of light, isolated from the spectrum, for example, red light alone, fell upon it. If the prism added color, a second passage should cause a further change of color. Yet the red light, after passing through the second prism, remained red. The prism was not adding color, it was only separating what was already present in white light. Newton also conducted the reverse experiment. Using a lens, he collected all the colors of the spectrum and directed them to a single point. The separated light, recombined, again yielded white. This was conclusive proof that white sunlight consists of a mixture of all the colors of the rainbow. What people had for millennia regarded as the simplest and purest form of light proved to be the most complex. Colors were not produced by contaminating whiteness. Whiteness was produced by mixing colors. This discovery had far-reaching consequences for the understanding of optical phenomena. The rainbow, which people had marveled at since the dawn of time, and which the mythologies of various cultures had wrapped in legend, at last found a scientific explanation. Raindrops acted as millions of tiny prisms, splitting sunlight into its component colors. The angle of refraction differed for different colors, which is why each hue reached the observer's eye from a different part of the sky, forming the characteristic arc. Newton did not stop at theoretical investigation of light. His inquiries also had a practical dimension, connected with the problems of astronomy of the day. Refracting telescopes, which, since Galileo's time had been used to observe the sky, had a serious defect. Lenses refracted different colors of light at different angles, which caused the images of stars and planets to be surrounded by colored fringes and never perfectly sharp. This phenomenon, called chromatic aberration, constituted a fundamental limitation on observational capabilities. Newton understood that chromatic aberration was an unavoidable consequence of the nature of light and the way lenses refract it. He concluded that the problem could not be solved by improving lenses. Instead, he proposed a radically new approach. Rather than refracting light in a lens, one could reflect it in a mirror. Reflection, unlike refraction, acts identically for all colors and does not cause chromatic aberration. In 1668, Newton built by hand the first reflecting telescope in history, later known as the Newtonian telescope, or reflecting telescope. It was a small device, with a mirror diameter of barely about 3.5 centimeters, yet the quality of its image far surpassed refracting telescopes of comparable size. Light entering the tube was reflected off a concave primary mirror, then off a small flat mirror placed at an angle, and reached an eyepiece mounted on the side of the instrument. This design, though simple in principle, required extraordinary practical skills. Newton ground the mirror from metal himself, constructed the tube and mount himself, and made all the components of the precision mechanism himself. The years spent in the apothecary's workshop in Grantham, building clocks and mills, now bore fruit in the form of abilities that allowed him to turn theoretical ideas into a working device. News of the young scholar's discoveries from Cambridge began to circulate in scientific circles. In 1672, Newton was invited to present his telescope before the Royal Society in London, the most important scientific institution in England. The Society, founded barely a decade earlier under the patronage of King Charles II, had gathered the most eminent scholars of the age and provided a forum for the exchange of ideas and the presentation of discoveries. The presentation of the telescope was a great success. Members of the Royal Society were impressed both by the innovative design and by the quality of image it provided. Shortly afterwards, Newton was admitted to membership of this prestigious institution. It was a pivotal moment in his career. From a provincial scholar working in isolation, he became a recognized member of the English scientific elite. Encouraged by this reception, Newton decided to publish his research on light and colors. In February 1672, he presented to the Royal Society a paper entitled, "A New Theory About Light and Colors," in which he described in detail his experiments with the prism and the conclusions he had drawn from them. This paper, Newton's first scientific publication, appeared in the Society's journal and immediately aroused enormous interest. Not all reactions were enthusiastic, however. Newton's theory, though based on carefully conducted experiments, contradicted the views of many respected scholars. Robert Hooke reacted with particular sharpness, one of the most influential members of the Royal Society, who had himself been researching light and had his own theories on the subject. Hooke challenged Newton's conclusions and suggested that the young Cambridge scholar was misinterpreting the results of his experiments. Criticism from Hooke touched Newton deeply. The man who had struggled all his life with a sense of rejection and distrust of others perceived the scientific polemic as a personal attack. He replied with a lengthy letter, in which he refuted Hooke's objections point by point, but the exchange of views turned into a years-long dispute. Newton, discouraged by the necessity of defending his discoveries against critics, began to regret having decided to publish at all. He withdrew from scientific life and for many years refused to share his work with the world, fearing further attacks and conflicts. Robert Hooke was one of the most colorful and versatile figures of 17th-century English science. Born in 1635 on the Isle of Wight, he displayed from an early age extraordinary abilities, both theoretical and practical. He studied at Oxford, where he worked as assistant to the famous chemist Robert Boyle, helping him construct an air pump and conduct experiments with gases. His talent for designing and building scientific instruments quickly brought him recognition in scholarly circles. In 1662, when the Royal Society was founded, Hooke was appointed its curator of experiments. This position required him to prepare and carry out scientific demonstrations at every meeting of the Society, making him one of the central figures in London's scientific life. Hooke took this role extremely seriously, and for decades astonished members of the Society with the ingenuity and variety of the experiments he presented. The scope of Hooke's interests was impressive. He conducted research on the elasticity of bodies and formulated the law describing the relationship between force and deformation, still known today as Hooke's law. He constructed microscopes and was among the first to observe through them the cellular structure of plants, introducing the very term cell into science. He occupied himself with geology, paleontology, architecture, mechanics, and astronomy. After the Great Fire of London in 1666, he participated in the rebuilding of the city, designing many buildings. He was a man of encyclopedic knowledge and tireless mind. Yet this versatility had its price. Hooke scattered himself among dozens of projects, rarely bringing any to completion. Many of his ideas remained in the form of sketches and notes, never published or developed systematically. This bred frustration that grew when other scholars arrived at similar conclusions and received the credit. Hooke repeatedly claimed that others had stolen his ideas or attributed his discoveries to themselves. In time, he became a jealous, suspicious, and quarrelsome man. The dispute with Newton over the theory of light was only the beginning of a years-long conflict between the two scholars. Hooke considered himself an expert in optics and could not reconcile himself to the fact that a young, unknown provincial from Cambridge had dared to challenge established views. His criticism of Newton's theory was sharp and at times malicious. He suggested that the prism experiments proved nothing and that the conclusions Newton had drawn were hasty and unjustified. Newton, who found criticism difficult to accept at the best of times, reacted to Hooke's attacks with fury. In his replies, he defended himself point by point, but the tone of his letters betrayed deep resentment. The correspondence between the two scholars became increasingly tense, and the exchange of scientific arguments degenerated into personal hostility. Newton began to regard Hooke as his chief enemy in the scientific world, a man who, envying him his success, deliberately made his life difficult. The conflict sharpened when Hooke began to claim priority over some of Newton's discoveries. He maintained that it was he who had first conceived the idea that gravitational force decreases in proportion to the square of the distance, and that Newton had merely developed his idea. In reality, the situation was more complicated. Hooke had indeed pursued his own reflections on the nature of gravity, and in correspondence with Newton had mentioned the inverse square law. However, he had never been able to prove this law mathematically, or to derive its consequences for the motion of planets. It was Newton who achieved the great breakthrough, combining intuitions about the nature of gravity with a precise mathematical apparatus. The matter came to a head in the mid-1680s when Newton was working on his principal work. Hooke publicly demanded recognition of his contribution and threatened to accuse Newton of plagiarism. Newton was furious. In a letter to Edmund Halley, who was mediating between the quarreling scholars, he wrote bitter words about Hooke, accusing him of wanting to reap the laurels for work he had not done. He stated that Hooke was a man who promised much, but finished nothing, and who, envying others their success, sought to diminish their achievements. In the end, Newton yielded on one point. In his great work, he included a mention acknowledging that Hooke, alongside Christopher Wren and Edmund Halley, had independently arrived at the inverse square law. This was, however, minimal recognition, phrased in a way that emphasized rather than diminished Newton's advantage. Newton made it clear that intuition or hypothesis alone means nothing without mathematical proof and the systematic development of a theory. The conflict with Hooke left deep marks on Newton's psyche. The scholar became yet more distrustful and suspicious, yet more reluctant to share his discoveries. For many years he delayed the publication of further works, fearing new attacks and disputes over priority. At the same time, he harbored a resentment against Hooke that did not fade even with the passage of years. Newton was a man who did not forget slights and could wait for the right moment to settle scores. That moment came after Hooke's death in 1703. Newton, who by that time was already president of the Royal Society and the most powerful figure in English science, used his position to systematically erase the memory of his old rival. The only known portrait of Hooke that had hung in the Society's headquarters disappeared. Historians debate to this day whether this was an accident or a deliberate act by Newton. Many of Hooke's works and instruments were dispersed or destroyed. His contribution to the development of science, though enormous, long remained undervalued and forgotten. The rivalry between Newton and Hooke was something more than a personal vendetta between two difficult personalities. It reflected deeper tensions in 17th-century science, where questions of priority and attribution of authorship were poorly defined, and the boundary between inspiration and plagiarism remained unclear. Scholars often worked on similar problems, independently arriving at similar conclusions, and then quarreled fiercely over who was first. The system of scientific publication was still taking shape, and the rules for awarding credit for discoveries were the subject of constant dispute. Hooke, despite all his faults, was an outstanding scholar whose contribution to the development of science deserves recognition. He was one of the fathers of the modern experimental method, a master in constructing scientific instruments, and the author of hundreds of ideas that were ahead of their time. His tragedy lay in his lack of patience and systematicness to carry his intuitions through to conclusion. Newton, for all his character defects, was capable of working on a single problem for years, not resting until he had achieved a perfect solution. Ultimately, history awarded the palm to Newton. It is his name that appears in textbooks, his laws that successive generations of students learn, his telescope that revolutionized astronomy. Hooke, long almost forgotten, has only in recent decades received a fairer assessment from historians of science. He was more than merely Newton's rival and critic. He was a scholar who, in his own way, contributed to the birth of modern science, though his contribution long remained in the shadow of his great rival. In 1684, Edmund Halley, a young and talented English astronomer, paid a visit to Isaac Newton in Cambridge. Halley, who would later become famous as the discoverer of the periodicity of a certain well-known comet, was at that time absorbed in a problem over which the most eminent scholars of the age had been puzzling fruitlessly. The question was the mathematical explanation of the motion of the planets around the Sun, in accordance with the laws discovered by Kepler. Everyone sensed that the key lay in a gravitational force diminishing with the square of the distance, but no one was able to prove this. Halley asked Newton directly what shape the orbit of a planet would take if it moved under the influence of a force inversely proportional to the square of the distance from the Sun. Newton replied without hesitation that it would be an ellipse, exactly as Kepler had described. The astonished Halley asked how Newton knew. He replied calmly that he had calculated it years before. When asked to show the calculations, Newton began searching among his papers but could not immediately find them. He promised to send the proof later, and kept his word. Several months later, Halley received a short treatise entitled On the Motion of Bodies, containing fundamental propositions of celestial mechanics. Halley immediately understood that he held something groundbreaking in his hands. He traveled again to Cambridge and begged Newton to expand his ideas into a full, systematic work. Newton, though initially reluctant, allowed himself to be persuaded. For the next 18 months, he worked with almost manic intensity, often forgetting to eat and sleep, completely absorbed in committing to paper what he had for years been storing in his head. The result was a work that was to change the face of science forever. Mathematical Principles of Natural Philosophy, such was the title Newton gave his work, appeared in print in July 1687. Publication was possible only thanks to Halley, who not only persuaded Newton to write the book, but also financed its printing from his own pocket, when the Royal Society withdrew from its promise to cover the costs. Without Halley's determination and generosity, the work might never have seen the light of day. The structure of the book was monumental. Newton divided it into 3 books, preceded by extensive definitions and axioms. The first book dealt with the motion of bodies in a vacuum, presenting a mathematical description of motion under central forces. The second book addressed the motion of bodies in resisting media, analyzing questions of hydrodynamics and fluid mechanics. The third book, entitled The System of the World, applied the tools developed earlier to the description of the actual universe, explaining the motion of planets, moons, comets, and ocean tides. The language of the work was extraordinarily difficult, even by the standards of 17th-century science. Newton deliberately chose a geometrical rather than algebraic form, claiming later that he wished to make reading difficult for those insufficiently prepared, in order to avoid incompetent criticism. Each proposition was formulated with rigor and proved by the methods of synthetic geometry, which required enormous intellectual effort from the reader. Many of Newton's contemporaries admitted that they were unable to understand the work in its entirety. The foundation of the entire structure was the 3 laws of motion that Newton formulated at the outset of the work as axioms. The first law concerned inertia, the second, the proportionality of force and acceleration, the third, the equality of action and reaction. From these 3 simple principles, Newton derived the entire edifice of mechanics, showing how they could explain innumerable natural phenomena. The culmination of the work was the law of universal gravitation, presented in the third book. Newton demonstrated that the force keeping planets in their orbits is the same force that causes apples to fall from trees. He calculated the motions of all the planets then known, and their moons, showing that they are all subject to the same laws. He explained why the orbits of the planets are ellipses, why planets move more quickly near the Sun, why the ratio of the cubes of distances to the squares of orbital periods is constant for all planets. Particularly impressive was his explanation of ocean tides, which had long been a puzzle for scholars. Newton showed that tides result from differences in the gravitational pull of the Moon and the Sun, acting on different parts of the Earth. The side of the Earth facing the Moon is attracted more strongly than the center of the planet, and the center more strongly than the opposite side. These differences cause the ocean to bulge on both the side facing the Moon and the opposite side, which explains why 2 high tides and 2 low tides occur in the course of a day. Newton also addressed comets, the heavenly bodies that had for centuries aroused fear and superstition. He showed that comets move in the same conic sections as planets, subject to the same laws of gravity. Their orbits are, however, highly elongated ellipses, or even parabolas, which is why they appear in the sky, rarely and unpredictably. Halley, using Newton's methods, later calculated the orbits of many comets and predicted the return of one of them, which today bears his name. The response of the scientific world to the Principia was divided, but enthusiasm gradually prevailed. In England, the work quickly acquired the status of almost a sacred text of science. On the continent, where the Cartesian vision of physics based on vortices of matter filling space prevailed, the reception was cooler. Many scholars could not reconcile themselves to Newton's concept of gravity as a force acting at a distance without any material intermediary. Leibniz himself ironized that Newton's gravity was something in the nature of a miracle or an occult quality, explaining nothing. Newton was aware of these objections and admitted himself that he could not explain the mechanism of gravity's action. In a famous passage, he wrote that he frames no hypotheses, using a Latin formulation that became the motto of the positivist approach to science. He did not know what gravity was, or how it acted at a distance through empty space. He knew, however, that his equations described the observed phenomena perfectly, and that was enough for him. The question of the nature of gravity he left to philosophers or future generations of scholars. The publication of the Principia was a turning point not only in Newton's biography, but in the entire history of science. For the first time, someone had presented a coherent, mathematical description of the operation of the entire universe, from falling stones to the most distant planets. The old division between terrestrial and celestial physics, inherited from Aristotle, was definitively abolished. The cosmos proved to be one great mechanism, operating according to unchanging laws that the human mind is capable of discovering and describing. Newton's work became the model for all later natural sciences. Over the next 2 centuries, scholars tried to emulate his method, seeking mathematical laws governing electricity, magnetism, heat, and chemistry. Newtonian mechanics remained the unassailable foundation of physics until the early 20th century, when Albert Einstein showed that at very high speeds and in very strong gravitational fields, Newton's laws require modification. Yet even today, in the age of relativity theory and quantum mechanics, Newton's equations remain an excellent approximation for the vast majority of practical applications. Gottfried Wilhelm Leibniz was born in Leipzig in 1646, 4 years after Newton. He was the son of a professor of moral philosophy, and from his earliest years displayed extraordinary intellectual abilities. At the age of 15, he began university studies, and at 20 he obtained a doctorate in law. But law was only one of many fields of his interest. Leibniz occupied himself with philosophy, logic, theology, history, linguistics, geology, and of course mathematics. He was the last great scholar who could realistically aspire to encompass the entirety of human knowledge. Unlike Newton, who spent his whole life in England, Leibniz was a man of Europe. He traveled throughout the continent, corresponded with hundreds of scholars and diplomats, and served as an advisor at the courts of German princes. He was a member of scientific academies in Paris, London, and Berlin, the last of which he himself founded. His ambitions ranged far beyond science. He dreamed of uniting the churches, creating a universal logical language, and reconciling the quarreling nations of Europe. The paths of Newton and Leibniz crossed for the first time in the 1670s. Leibniz, residing in Paris, became interested in mathematical problems that had long occupied scholars. These concerned calculating the areas of figures with curved boundaries, finding tangents to curves, and describing quantities changing in a continuous manner. These questions, which we today classify under the differential and integral calculus, lay at the limits of contemporary mathematical capability. Leibniz worked on these problems independently, and within a few years, created a coherent mathematical system, which he called the differential and integral calculus. He introduced a notation that proved extraordinarily intuitive and practical. The symbols he used, such as the integral sign, and the notation of derivatives using the letter d, are employed to this day, while Newton's notation, based on dots placed above variables, has been largely abandoned. Leibniz published his results in 1684 and 1686 in scientific journals, some years before Newton's Principia appeared. The problem was that Newton had developed very similar methods much earlier, during his stay at Woolsthorpe in the 1660s. His method of fluxions, as he called it, He continued developing over the following years, but in keeping with his custom did not publish his results. Only a narrow circle of acquaintances knew of his discoveries from fragmentary mentions in letters and unpublished manuscripts. When Leibniz announced his work, Newton was convinced that the German must somehow have acquainted himself with his ideas and appropriated them. Initially, relations between the two scholars were cordial. They exchanged a few polite letters in which each expressed respect for the other's achievements. Newton, in the first edition of his Principia, even included a mention acknowledging the independence of Leibniz's discovery. In time, however, the atmosphere began to sour. Supporters of both scholars began to compete for priority for their masters, and scientific exchange degenerated into a bitter battle for honor and fame. The conflict sharpened at the beginning of the 18th century. In 1699, the Swiss mathematician Nicolas Fatio de Doulier, a close friend of Newton, publicly accused Leibniz of plagiarism. He claimed that Leibniz, during a visit to London in 1673, had access to Newton's unpublished manuscripts and had stolen key ideas from them. Leibniz was outraged and demanded an apology, but did not receive one. Newton remained silent, but behind the scenes stoked the conflict, supplying his supporters with arguments and documents. In 1711, the dispute reached its climax. Leibniz lodged an official complaint with the Royal Society, demanding to be cleared of the charge of plagiarism. The Society appointed a committee to investigate the matter and deliver a verdict. At the head of this committee stood none other than Newton himself, who by that time was already president of the Society. This was a glaring violation of the principle of impartiality, but no one dared to protest against the most powerful scholar in England. The committee, led by Newton and composed of his loyal supporters, worked for only a few weeks. In 1712, it published a report entitled Commercium Epistolicum, containing a selection of correspondence and documents purporting to prove Newton's priority. The verdict was unequivocal and devastating for Leibniz. The report stated that Newton had discovered the calculus first, and that Leibniz had probably drawn on his unpublished works. Newton personally wrote an anonymous review of the report, in which he accused Leibniz even more forcefully of dishonesty. Leibniz defended himself until the end of his life, publishing his own explanations and refuting the charges. He pointed out that his notation and approach differed significantly from Newton's, which bore witness to the independence of his discovery. He emphasized that it was he who had published his results first, while Newton had kept his in a drawer for decades. He argued that even if Newton had genuinely made his discovery earlier, unpublished knowledge cannot form the basis for claims of priority. The dispute had tragic consequences for both sides and for science as a whole. Leibniz died in 1716, embittered and alone, almost forgotten at the court he had faithfully served for 40 years. Newton, though officially victorious, harbored resentment to the end of his life, and in private conversations boasted that he had broken Leibniz's heart. It was a triumph that brought him no honor. The long-term consequences of the conflict were, however, even more serious. English mathematicians, loyal to Newton, stubbornly clung to his notation and methods, rejecting everything that came from Leibniz. Meanwhile, mathematicians on the continent, especially in France and in German-speaking lands, adopted Leibniz's much more flexible and practical notation. For over 100 years, English mathematics developed in isolation from the main European current, resulting in a marked lag behind the continent. From a historical perspective, the dispute over priority seems largely futile today. Modern historians of science agree that both Newton and Leibniz made their discoveries independently of each other. Both drew from the same mathematical heritage, both wrestled with the same problems, and both found similar solutions. Such convergences are nothing unusual in the history of science. Great discoveries often arise simultaneously in many places when the time is ripe and the intellectual tools are available. Newton and Leibniz independently created one of the most powerful mathematical tools in human history. The differential and integral calculus made it possible to describe motion, change, and continuity in a way that had previously been impossible. Without it, there would be no modern physics, engineering, or economics. Both scholars deserve recognition as co-creators of this fundamental achievement, regardless of which of them was first by a few years. In 1696, 53-year-old Newton made a decision that surprised the scientific world. After 35 years spent within the walls of Cambridge, he resolved to leave the university and move to London. The reason was prosaic, though surprising for someone of his standing. The great scholar, author of the Principia, accepted the position of warden of the Royal Mint. To many it seemed a descent from the heights of science into the world of bureaucratic administration. The reasons for this decision were complex. Newton had for years been struggling with periods of deep depression and nervous breakdowns. He went through a particularly severe crisis in 1693, during which he suffered for several months from insomnia, paranoia, and fits of rage that alarmed his few friends. Some historians speculate that the cause may have been chronic mercury poisoning from the mercury Newton used in his alchemical experiments. Others point to the deep loneliness and emotional instability that had accompanied him since childhood. Whatever the cause, Newton needed a change. The post at the Mint was arranged for him by Charles Montague, Lord Halifax, an influential politician and former Cambridge student who admired Newton and wanted to provide him with financial security. The position of warden was traditionally treated as a sinecure, a comfortable post requiring minimal engagement, but yielding a quite decent income. Most previous wardens had treated their duties in a purely formal manner, appearing at the Mint occasionally to sign documents. Newton approached his new role quite differently. With the same intensity with which he had previously investigated the laws of planetary motion, he threw himself into a whirl of administrative work. He moved into a residence within the Mint complex at the Tower of London and began spending most of his time there, personally overseeing every aspect of the institution's activities. His pedantry and inflexibility, which had previously manifested themselves in scientific disputes, now found an outlet in ruthless enforcement of standards and regulations. The moment at which Newton took up his post was particularly critical for English finances. The country faced a serious monetary crisis. For decades, silver coins had been systematically clipped and filed by dishonest people who collected the precious metal shavings. As a result, most of the coins in circulation weighed considerably less than they should, which undermined confidence in the currency and destabilized trade. The government decided to carry out a great recoinage, replacing the old, debased coins with new ones of full weight and with a milled edge that made clipping more difficult. Newton faced an enormous logistical challenge. Millions of new coins had to be produced in a short time, the old ones withdrawn from circulation, and the entire operation conducted without causing the financial system to collapse. The scholar who had hitherto occupied himself with abstract mathematical problems proved a surprisingly effective administrator. He reorganized the production processes at the Mint, introduced new machines and procedures, and increased the productivity of workers. Under his direction, the production of coins increased several-fold, reaching levels unprecedented in the history of the institution. Newton did not, however, limit himself to improving production. With the obsessiveness characteristic of him, he threw himself into the fight against counterfeiters, who were a plague of 17th-century England. Counterfeiting money was at that time a capital offense, but the high profits and relatively low risk of detection attracted hordes of criminals. Newton treated the pursuit of counterfeiters as a personal mission. He personally interrogated suspects, hired spies and informers, and visited prisons and taverns in search of evidence. For a man who had spent his entire life avoiding contact with people, this was a surprising engagement in the dirtiest corners of the London underworld. The most famous victim of Newton's efforts became William Challoner, a bold fraudster and counterfeiter who had for years evaded justice through cunning and patronage. Challoner went so far as to accuse the Mint itself of incompetence and corruption, presenting himself as an expert who could help reform this system. Newton recognized him as a dangerous enemy and spent 2 years collecting evidence, patiently building the case. When he finally managed to bring Challoner before the court, the verdict was foregone. The counterfeiter was condemned to death and hanged in 1699. Newton personally ensured that justice was done. In 1699, Newton was promoted to the position of Master of the Mint, the highest rank in the institution. He held this post until the end of his life, for nearly 3 decades. Under his direction, the mint became a model of efficiency and integrity, and the English monetary system gained a stability that contributed to the economic development of the country in the following century. Alongside his work at the mint, Newton consolidated his position in the scientific world. In 1703, he was elected president of the Royal Society and held this function for 24 years until his death. His presidency was a time of both flourishing and of authoritarian rule. Newton treated the society as his personal kingdom, tolerating no dissent and dealing ruthlessly with anyone who dared to oppose him. At the same time, however, he cared for the prestige of the institution and promoted young, talented scholars. In 1704, Newton finally published his work on optics, on which he had been working at intervals for more than 30 years. Optics, as the book was entitled, differed significantly from the Principia. It was written not in Latin but in English, making it accessible to a wider circle of readers. Instead of a dry geometrical exposition, it contained vivid descriptions of experiments that the reader could repeat independently. Newton deliberately addressed this work to beginning researchers, wishing to spread the experimental method among his countrymen. The book was an enormous success and consolidated Newton's position as an unquestioned scientific authority. In 1705, Queen Anne honored him with a knighthood. The ceremony of investiture took place in Cambridge, at the university Newton had left years before but which remained the symbolic place of his scientific triumphs. Sir Isaac Newton became the first scholar in history to receive a knighthood for scientific achievements. Some historians suggest that the Queen's decision had political undertones as well, but whatever the motivation, it was an unprecedented distinction. In his London period, Newton became a prosperous and influential man. He bought an elegant house, surrounded himself with servants, and led a life befitting a member of the upper classes. Young scholars treated him with almost religious veneration, vying for the opportunity to meet him and converse with him. Counterfeiters trembled at the sound of his name. Members of the Royal Society did not dare oppose him. Newton, once a lonely and timid provincial, had become one of the most powerful figures in English public life. He also engaged in charitable activities, providing financial support to numerous relatives and responding to letters from people seeking help. This generosity, contrasting with his ruthlessness toward scientific rivals and criminals, creates the picture of a complex man full of contradictions. Newton could be both cruel and magnanimous, both vengeful and generous. His character remained a mystery to his contemporaries, as it remains a mystery to historians today. Beyond his scientific work and administrative duties, Newton throughout his life devoted an enormous amount of time to 2 fields that remain a puzzle for many biographers. The first was alchemy, the art of seeking the philosopher's stone and transforming base metals into gold. The second was theology, especially biblical chronology and the interpretation of prophecy. In both fields he left behind thousands of pages of manuscripts, which for centuries were concealed from the world as the embarrassing secret of the great scholar. His interest in alchemy had accompanied Newton since his days at Cambridge. For decades he conducted experiments in his laboratory, carefully noting recipes, observations, and conclusions. He built furnaces, distilled substances, mixed mercury with other metals, seeking the mysterious materia prima, from which, according to alchemists, all substances are composed. His alchemical notes, often written in code or by means of allegorical symbols, occupy more space than all his scientific works put together. For modern researchers, Newton's engagement in alchemy appears to be a paradox. How could a man who created modern physics based on mathematics and experiment simultaneously believe in the mystical search for the philosopher's stone? The answer is more complex than it might seem. In the 17th century, the boundary between alchemy and chemistry was fluid, and many serious scholars treated alchemical experiments as a legitimate form of studying nature. Newton believed that the ancient sages had possessed deep knowledge about the nature of matter, which had been encoded in allegorical texts and passed down from generation to generation to the select and initiated. Theological study was for Newton equally important, and perhaps even more important than natural scientific research. Raised in the Protestant tradition, he had from an early age treated the Bible as the supreme authority in matters of faith and morality. Yet his interpretations of Scripture deviated significantly from the official doctrine of the Church of England. Newton came to believe that the dogma of the Holy Trinity, the foundation of Western Christianity, was a later distortion of the original faith. He believed in one God, and rejected the divinity of Christ in the orthodox sense of the term. These views, known as Arianism, were in 17th-century England a heresy punishable by the loss of posts, and potentially even by imprisonment. Newton never publicly revealed his religious convictions, keeping them secret even from his closest friends. When he took up a chair at Cambridge that required swearing an oath of allegiance to Anglican doctrine, he obtained a special exemption from the king, by which he avoided the necessity of taking holy orders. Throughout his life, he balanced on the edge between public conformism and private revolt against religious orthodoxy. In his later years, Newton devoted ever more time to biblical chronology, attempting to establish the exact dates of events described in the Old and New Testaments. He combined analysis of sacred texts with astronomical knowledge, using heavenly phenomena as reference points for dating historical events. The work on these questions absorbed him until his final days, though its results met with a mixed reception among his contemporaries. The early years of the 18th century brought a gradual deterioration in the health of the aged scholar. Newton suffered from kidney stones, which caused attacks of painful colic. Despite this, he refused to resign from his duties, and continued regularly to chair sessions of the Royal Society and to oversee the work of the Mint. When doctors recommended he use a sedan chair for getting about, he firmly refused, insisting that he would walk under his own power as long as he had the strength. In 1724, at the age of 82, Newton faced an unexpected challenge. In France, without his consent, fragments of his work on biblical chronology were published, accompanied by critical commentary. Despite his advanced age, the scholar reacted with characteristic energy and ferocity. He wrote an extensive reply in which he refuted his critics' objections point by point. He also set about preparing a complete edition of his chronology, on which he worked until his final days. During this same period, Newton began to put his papers and manuscripts in order. He decided to destroy some of them. For several days he burned whole boxes of documents in the fireplace. Documents he considered unsuitable for preservation for posterity. What exactly went up in flames remains a mystery. Some historians speculate that these were personal letters whose disclosure Newton did not wish. Others suggest they may have been alchemical notes or heretical theological reflections. Some researchers even claim that Newton destroyed documents compromising his conduct in the disputes with Hooke and Leibniz. On the 2nd of March 1727, Newton chaired a meeting of the Royal Society for the last time. According to witnesses, he looked well and was in good spirits. But the next day he fell ill, and took to his bed with severe abdominal pains. Doctors determined that a kidney stone that had troubled him for years had moved and was blocking the urinary tract. The prognosis was pessimistic. For the next 2 weeks, Newton struggled with unbearable pain, occasionally losing consciousness. On the 20th of March, 1727, at the age of 84, Sir Isaac Newton died at his home in Kensington. No close family were at the bedside, since Newton had never founded one. He was attended only by servants and doctors. The funeral was conducted with honors befitting a monarch. Newton's coffin was laid out in the Jerusalem chamber of Westminster Abbey, where for several days the inhabitants of London could pay their last respects. The chronicles record that the crowds were enormous. In the funeral cortege walked lords, bishops, scholars, and the kingdom's highest officials. Newton was buried in Westminster Abbey, the necropolis of kings, and the most distinguished sons of England. On his tomb was placed a Latin inscription proclaiming that here rests one who, with an almost divine mind, first explained by the force of his genius the motions and figures of the planets, the paths of comets, and the tides of the oceans, who investigated the differences in rays of light and the properties of the colors arising therefrom, which no one had previously suspected. An industrious, sagacious, and faithful investigator of nature, antiquity, and scripture, he confirmed in his philosophy the majesty of God Almighty, and expressed in his conduct the simplicity of the gospel. Let mortals rejoice that there existed such and so great an ornament of the human race. Newton's scientific legacy is immeasurable. His three laws of motion and the law of universal gravitation form the foundation of classical mechanics, which for over 200 years remained the unassailable edifice of physics. His work on light laid the foundations of modern optics. His method of fluxions, developed in parallel by Leibniz, became an indispensable tool for mathematicians, physicists, and engineers. Every bridge, every aeroplane, every space rocket is a monument to his genius. Yet Newton was something more than just a great scholar. He was a profoundly complex man, full of contradictions, whose personal life was marked by loneliness, conflicts, and secrets. At the end of his life he compared himself to a boy playing on the seashore, rejoicing at finding a smoother pebble or a prettier shell, while the great ocean of truth lay undiscovered before him. This metaphor, full of humility and wonder before the unknown, remains one of the most beautiful images ever created by a scholar speaking of his own work. I thank you for listening to this story of Isaac Newton, the man who changed our understanding of the universe. If this story has appealed to you, I encourage you to leave a comment and like this video. I also invite you to subscribe to the channel, where further fascinating stories about great figures of history await you.